Third time's a charm. All right, cool. So let's get started. We have one last topic to discuss to close out Unit 1. And these are a functional group that are very similar to alkenes, so they're lumped into the same category. We're going to be talking about alkynes. All right, remember alkanes were all single bonds. Alkenes had a double bond. What are alkynes? They got a triple bond, right? So these are, again, molecules with only carbons and hydrogens, but they contain at least one triple bond. And I guess specifically carbon-carbon triple bond. All right. So in terms of our structure of alkynes rather, we see something that's fairly similar to what we saw for alkenes. We have a carbon-carbon triple bond here. If these two carbons are triple bonded together, how many hydrogens should there be on each of them?
One.
Just one, right? They already got their 3 bonds. Okay. So importantly, when we talked about alkenes, we talked about how a lot of the reactions of alkenes, a lot of our understanding of alkenes comes from the structure of that extra bond, right? We see the same sort of thing with an alkyne. One of those bonds are one of those boring sigma bonds that don't really have much reactivity to them at all. But the other two are those special pi bonds, right? So that cloud of electrons is extending out above and below and in both directions. So one pi bond will sort of extend above this molecule. Again, it's the overlap of those peanut-shaped orbitals. The other one is going to be pointed perpendicular. So now we'll have another electron cloud, another peanut-shaped cloud. And I know my artistry is not great here, but it is extending perpendicular to that other one. Okay, so just to get rid of these sort of squiggly lines where our bonds are. Right? The bottom line is, again, we have electron clouds that are very easily accessible, right? They're not sitting between these two carbon atoms, but they're sitting outside of that molecule. We talked about how the geometry of an alkene was that it was flat. It was that trigonal planar geometry, all right? We're going to see something similar, but instead of forming a triangle, because there are 3 bonds, now we only have 2 bonds. So this is going to be what we call a linear geometry, right? These carbons are sp hybridized. Okay, you can say alkynes have a linear geometry. All right, specifically about that carbon-carbon triple bond. So all 4 of these atoms are situated all in a straight line in our alkyne. All right, if we choose a little bit more complicated of a structure here, let's put a bunch of carbons. We'll put a bunch of single bonded carbons. And then we'll add this triple bonded carbon on the end here. Okay. Fill in my hydrogens. Okay, importantly, I'm not going to put any hydrogens on this carbon here, right? It's already got its 4 bonds associated with it. All right, so looking at this more complicated structure here, we can say which atoms are all in this line, are in this linear fashion here. Okay, it'll be those 2 carbons about that triple bond, as well as the 2 atoms, 1 on each side, that they are bound to. All 4 of these atoms in this molecule will appear in this straight line. Okay, so this is really important for how we draw the bond line structure of our alkynes. Is unlike our alkenes and our alkanes, where we always have that zigzaggy structure. Here, when we draw in that triple bond, we have to be really good to keep those atoms in a straight line. All right, so our bond line structures of our alkynes . Okay, importantly, what we're going to see is they have to show that linear geometry about that carbon-carbon triple bond. All right, so I'm going to represent this same molecule here. We got 4 carbon alkyne here. Here's our Lewis structure. I'm going to put this into a bond line structure. All right, and I'm going to start with my normal kind of zigzag here. All right, but then this carbon is going to be a part of that linear triple bond. So now my next 3 bonds I have to draw all in a straight line here. Okay, so just like we sort of showed in our Lewis structure, we have these 1, 2, 3, 4 atoms that are all sitting in a straight line here. Let me put them side by side so it's a little bit easier to see. Okay, now you gotta be careful. This is something where your homework will totally let you get away with doing it incorrectly and doing it as a zigzag, but on an exam, I'm gonna ask you to draw, I'm telling you right now, one of the questions on the exam, I'm gonna ask you to draw a structure of an alkyne. If you don't draw it in this linear way right here, you're not gonna get the points for that structure, all right? So again, about that triple bond, those atoms have to be in a straight line. To be clear, the one thing that I could have omitted from this picture here was that hydrogen on the very end, because our hydrogens are allowed to be implied. I wanted to put it there to keep in mind that we have those 4 atoms, but hydrogens are always allowed to be implied.
That was my question.
Cool. All right, so then for the sake of practice here, you're going to give me the bond line structure for the following molecule. Right? I'm giving you a Lewis structure. Turn that into a bond line structure for me. All right, count your carbons. Remember, tappa, tappa, tappa. Make sure you got the correct number of carbons in your molecule. All right, and specifically when I draw this, I'm going to draw these 4 atoms all in a straight line here. Okay, so start with my normal kind of zigzag structure, but now I've hit that first atom, so everything that comes afterwards is going to be all in a straight line. Okay. When we're doing our alkynes, this is because they're represented in this straight line here, people very often forget there are carbons, let's say, on either side of this triple bond here. All right, so what I've shown here is, again, my 1, 2, 3, 4 atoms, in this case all carbons, that are all in a line in this structure here. Okay, so when you're given a structure of an alkyne and you're counting your carbons, don't forget that on either side of that triple bond lives a carbon atom. What's up?
Don't you want 4 carbons before the double bond? Or 3?
Oh yeah, so 1, 2, 3, 4, 5 carbons total in that molecule. What's up?
Is there a specific orientation where it always has to be on the middle one? Like the middle line continues on the triple bond, on the bond line structure?
Yeah, typically, yes. So you will see you mean like the one that's not floating? Yeah, typically you wouldn't see it like that. Is that your question? Yeah, typically the little floating lines are in. I mean, that is not the end of the world, but yes, that is how you will see it represented. Okay, we got a new functional group. So the first thing we're going to do is learn how to name that functional group. Let's just go ahead and take that example that we had up here. All right, I'll get rid of my colors. Cool. What's step 1? Parent chain. All right, so when we were talking about nomenclature of alkenes, we had to introduce this new rule for our parent chain, which is that the parent chain must contain that functional group. Same thing goes for our alkynes, right? So we're looking for the longest continuous set of carbons that contains that functional group. Okay, in this case, we're talking about that carbon-carbon triple bond. All right, when we were talking about alkanes, what ending did we use? A-N-E. When we were talking about alkenes, what ending did we use? E-N-E. And when we're talking about alkynes, what ending do you think we use? Y-N-E. All right, they're not all that terribly creative. Okay, with regard to the substituents, there's nothing new to note here. All right, and then when we number our parent chain, the only thing that we're going to note is exactly what we had talked about with regard to alkenes, which is those functional groups, they get priority in your numbering scheme. All right, so when I number this molecule, the only thing I'm going to pay attention to is the location of that triple bond. All right, so again, functional groups get priority. All right, and then we will refer to the location of that triple bond with whatever number is lower. Same thing we did with alkenes. All right, really the only difference is you're changing that ENE ending to a YNE ending. So everybody take a second, given our example here, and see if you can't name this molecule. Given what we did with alkenes, we just have that one little twist that we threw on it here. I think the hardest part is just the thing I warned about at the beginning, which is the counting carbons. Make sure that you note that there are carbons on either side of that triple bond, right? So there's a total of 5 carbons in that molecule. We have to indicate where this triple bond is, so I'm going to number my parent chain. And which one of these numbering schemes am I going to go with, red or blue? Red. I'm going to put that triple bond at the lowest number. All right, and it's between carbons 2 and 3, so I'm going to refer to its position with the lower number, right? So this would be 2-pentyne. Okay, we have those 5 carbons in our parent chain, so that's where that pent prefix comes from. This is a triple bond now, so the ending that we will use is YNE, and we got to refer to the location of that triple bond with that locate number. Cool. All right, let's just practice this. Okay, so two important things. One important thing to note just about how the structures are drawn, right, is that they kind of look weird, right? They're not our normal zigzaggy structures. They're a little bit more elongated, and again, that's because about that triple bond, we have to draw those atoms all in a straight line here, all right? Like I said, I think counting carbons can be the trickiest part of this whole thing. So how many carbons do we have in the parent chain of this molecule? 7. 1, 2, 3, 4, 5. I gotta remember there's a carbon at the base of that triple bond. So 6, 7. And when I number this, I'm going to number it from right to left. So I get the lowest possible number for that triple bond. All right, so this would be 1 heptine. Okay. What about this next structure here? How many carbons in the parent chain? 6. 1, 2, 3, 4, 5, 6. I'm going to number my parent chain. 1, 2, 3, 4, 5, 6. Or go the other way. 1, 2, 3, 4, 5, 6. And which one of these numbering schemes am I going to pick? Red or blue? Right, because remember, the only thing I'm going to pay attention to is that triple bond. I don't care about my substituent. I don't care about this guy over here, what we would call a fluoro group. All right, the only thing I pay attention to is that triple bond. Okay, the very last step, and I didn't put it down here because there's nothing new to add, but remember we just assemble the name with those substituents out front. So when I put my name together, I'm still going to start with that 6 fluoro. And now I have my parent chain, which is the 2 hexyne. What's up?
So you don't count that as a 7?
It is not a carbon, no. So your parent chain, these will specifically refer to how many carbons there are in the parent chain. So the fluorine's a substituent. We account for that in the name out front here, but it's not what's going to factor into the prefix. Okay, when we talked about cyclic alkanes and we talked about alkenes, there was this extra pain in the butt thing that we had to pay attention to, what we called stereochemistry.
Is that one implied, or we have like one on the previous?
Sorry, what?
Previous one, like 1 heptine?
Oh, no, it is not implied because there's such a thing as 2 heptine and 3 heptine, right? So you would have a different molecule depending on where you put it in. It's only for rings that it would be when there's a substituent on a ring that's implied. Because if you picked it up and moved it, you would just change what carbon 1 is here. Here you have to, for any straight chain, you have to include it. Okay, stereochemistry of alkynes. Good news. We don't have any. There's nothing to worry about. There's no such thing as like cis and trans isomers. There's not that same sort of problem that we have with alkenes, because for an alkyne and that linear geometry, there's only one way that you can organize things in a line. You don't have that same sort of problem that we had, right? So because of our linear geometry, we do not have multiple ways to arrange these atoms. So cool, don't have to worry about it with regard to alkynes like we did with our alkenes. So then that leads us straight into our reactions of alkynes. All right, and what we're going to see is because alkynes are also consisting of those pi bonds, they're going to undergo the same types of reactions that alkenes undergo. What did we call that class of reactions? Addition reactions. So alkynes also undergo addition reactions. Okay? It's just that now that we have two pi bonds. All right, so let's take one of our addition reactions that we studied, these halogenation reactions. These are addition of a halogen where X is F, Cl, Br, or I. Okay, just like we noted before for our addition, our halogenation reactions, Cl and Br are the ones you're going to see the most common because they work the best. Maybe iodine in solution, but really very rarely fluorine. All right, and let's first lay this out with our Lewis structure here. All right, I'm going to react this with, for example, Br2. I'll draw out my full Lewis structure for bromine here. All right, the only thing that you're going to see that's a little bit different is now we have two pi bonds, so I can either add just one equivalent of bromine, or I could follow that up with a second equivalent of bromine. And we would get two different products here. Very similar, but two different products. See if you can't predict what those products would be based on what we discussed about addition reactions with alkenes. I'm sorry? No, the one's going to add one bromine molecule. The other one's going to add two bromine molecules. And I guess let's just remind ourselves real quick about this same reaction with our alkenes, right? These halogenation reactions. What happens is that pi bond in our molecule is broken, and we replace it with a new bromine carbon bond on either side, okay? What we're going to see is the exact same thing. Remember our alkynes, we have now two pi bonds. So in this first reaction, one of them will be broken. And I'm going to replace it with a bromine on either side. Okay, I'm just still left with one of those pi bonds here. So now my product after this first addition would be what functional group? It's got some bromines and a carbon-carbon double bond. So this is an alkene. It does have bromines on there, so it's like an halide. What doesn't matter? Doesn't matter, but it's got this carbon-carbon double bond. Let me be good and put in my lone pairs. Okay. In my second reaction, all that's going to happen is now that second pi bond is going to be consumed in this reaction. All right, so now I'm going to do the same thing with a second equivalent of bromine, and take a second and see if you can't predict what our products would be. Okay, so now we will have our halogenation of this carbon-carbon double bond. We already had one bromine on each carbon to begin with, and now with this second addition reaction, we have added another bromine. Okay, so after our first addition reaction here, we went from a carbon-carbon triple bond down to a carbon-carbon double bond and added a bromine to either side. And then we can react it with another molecule of bromine and do the same thing. We're going to now take our double bond down to just a single bond and put another bromine on either side. All right, so let's leave this up here and then see if by analogy we can't figure out what the hydrogenation reaction scheme would look like. Remember, this is now the addition of H2. All right, so again, we're going to start out with our alkyne. We're going to first react it with just one equivalent of H2. And then we're going to take that product and react it with a second equivalent of H2. I guess I can be really thorough and draw out my Lewis structure for H2. I will say that you do still need a catalyst. I'm just going to say catalyst. We're not going to get too bogged down in the differences in the catalyst you would use for alkenes or alkynes, other than to say you do need a catalyst. All right, so what functional group do we get after the addition of that first equivalent? Alkene. All right, we started out with an alkyne. If we add one molecule of H2, that means we're going to convert this first pi bond into now carbon-hydrogen single bonds on either side. We still have that original hydrogen on there. Okay, so to be clear, these are my hydrogens that I've just added. And then I'm going to add a second equivalent of H2, and this is going to give me what functional group? Alkane. All right, so now my carbon-carbon bond has been reduced to just a carbon-carbon single bond. I have those two orange hydrogens I originally stuck on there. I have the two that the molecule started out with. And now I have these two that have been added to either side of that carbon-carbon double bond. Cool? All right, so just like we saw for our alkenes, alkynes also have those pi bonds. The root of why alkenes undergo these addition reactions are because they contain those carbon-carbon pi bonds. Alkynes are the same. We just have now an additional one, right? So we can have not one, but two addition reactions with our halogenation or our hydrogenation. Okay. So, the one that I'm sort of going to focus on for the remainder of our class period here are the hydration of alkynes. And that's because these reactions both do exactly what you would expect in analogy with alkenes, but with this added sort of twist on there. All right? So first, let's go back and review some of these hydration reactions of alkenes that we talked about, because we learned about a few different ones, right? And the difference was where that hydroxyl group got placed on that ring. So one of those things that I told you that you can do to kind of help learn these reactions are to create a little reaction wheel. And so that's what we're going to do here. You're going to show me on one side the reaction that we would get with borane, NTHF, H2O2, NaOH. And on the other side, you're going to show me with that mercury business. Okay, and in these reactions, we have this big, ugly list of reagents here, right? It's not just H2 or something nice and convenient like that. We got a whole bunch of crap here. The good news is that this isn't anything that you have to memorize. You just have to be able to sight recognize these and know what they do, right? So first of all, the difference between these two reactions are which carbon about that double bond we're going to place that hydroxyl group. For the first one with the mercury, which one is it going to be on, the red or the blue carbon? The blue, and why the blue? More substituted, right? The more substituted carbon. So when I'm looking at this ugly list of reagents here, I just kind of blur my eyes and I see this mercury here. That's going to let me know that this is the more substituted carbon. That's the one thing we have to sort of remember. Okay. You know, again, you don't have to memorize that list. You're always going to see them together because that is in the lab how you would carry it out. Really, it's just a pain in the butt for me because I got to remember them for all of our practice problems to put down. You just got to be able to sight recognize it, right? We don't have to have these things memorized. Likewise, when I see this BH3 and THF with this hydrogen peroxide and sodium hydroxide, I kind of blur my eyes, and that boron lets me know that this would be prefer the less substituted carbon. That's what I have to remember about these two reactions here. So I'm going to add my water. These are hydration reactions. Again, in the first one, I'll keep my color coding the same, blue and red. When we say that this reaction prefers the more substituted carbon, it's because it's going to put the OH group on that more substituted carbon. The hydrogen gets added to the other. But when we use that fancy BH3, we get the OH group placed on the less substituted carbon, and my hydrogen goes on the other side. What's up?
This is alkynes. The hydration is
These are alkene. We're just showing alkenes. This is what we learned last week, and then we're going to extend this. We're going to see something very similar for alkynes.
We don't have to draw the hydrogen.
You do not have to draw the hydrogen, no. Because it was a new bond that was created, I put it in there to illustrate a point, but no, it would be the exact same structure if you left that implied hydrogen, if you left it implied. Okay, cool. So we got to keep this in mind. We're going to see something very similar in our alkynes here. We're going to see that there are certain hydration reactions that also contain mercury that prefer the more substituted carbon. And there are other hydration reactions with this boron that prefer the less substituted carbon. All right, but there's going to be this added, very fun twist that we're going to throw on this here. All right. So first of all, let's just do our very simple alkyne hydration using our 2-carbon alkyne and that drawn out Lewis structure. Okay, and I want you to predict what our product would be if you added just one equivalent of water to this structure here. right, so we're going to get rid of one of those pi bonds in my substrate. So now I'm left with a carbon-carbon double bond. On one side, we've added the hydrogen, and on the other side, we have added that OH group. In this case, it doesn't matter which side you picked. It was a symmetric molecule here. Okay? So this is what we would expect these hydration reactions to do based on analogy of what we saw with our alkenes. And indeed, this is what this hydration reaction does, all right? But unfortunately, it doesn't stop there. This thing that we created in the middle here is what's called an enol. What do we think the ene in our enol refers to?
Alkene.
That carbon-carbon double bond, all right? And the OL refers to that alcohol group. So an enol means we have a carbon-carbon double bond with an OH group on that carbon. All right. So our hydration reactions of alkynes, they do kind of what we would expect. They create these molecules here, but these enols are unstable. And they will immediately rearrange themselves. All right, so one thing that I just want to point out here that we're going to, is the formula of this molecule that we've just created has 4 hydrogens, 2 carbons, and an oxygen. So C2H4O. What's going to happen is we're not going to add any new molecule or atoms. We're not going to take away any atoms. We're just going to rearrange what's on the page already here. All right? So what's this is going to rearrange into is a carbon-carbon single bond. And that carbon-oxygen single bond becomes a carbon-oxygen double bond. This molecule has that same formula, C2H4O, right? So again, I didn't add any new atoms. I didn't take any atoms away. I rearranged what was on the page here, all right? And specifically what you can see is that I moved that pi bond from being a carbon-carbon pi bond to now a carbon-oxygen pi bond. All right? This is now an aldehyde, maybe a ketone depending on what we started with. All right? So our enols will rearrange themselves into aldehydes or ketones, both functional groups that contain that carbonyl bond, that carbon-oxygen double bond. All right, so we have a new carbon-oxygen double bond.
The first one on our original alkene, is that an isomer to where you can switch it the opposite way, or that's
Say that again?
like
This one right here that we're looking at?
Yeah. Like, wouldn't you get 2 different products? Or like there's 2 different ways to write it since the double bond can't be rotated?
In this case, because this carbon has 2 hydrogens, there'd only be one way to draw it. There can be, I could have chosen an alkyne that might give us 2 isomer products. You don't have to worry about that, all right? To be clear, yes, certain reactions will generate a mixture of cis and trans isomers. I'm not going to go too crazy on that. What I expect y'all to be able to do is if I give you an alkene and say, is this cis or trans, you can tell me which one it is. When it comes to drawing products of a reaction, if you gave me one or the other, I'd be perfectly fine with it, all right? Truthfully, there's a mixture of both, and in the second, the longer course, you might learn about how one's more stable than the other. We're not really going down the stereochemistry road quite as crazy as we could, all right? So if we did do in a reaction where you could draw either a cis or trans product, just give me one of them, all right? What I'm really concerned with is that you know where these new bonds are being formed. Okay, we got enough craziness going on without me complicating things anymore, right? So in our hydration reactions, our actual product isn't going to be this enol that you would expect, but rather you're going to get an aldehyde or ketone after this rearrangement step right here. We have a very fancy word for these internal rearrangements that occur. These are tau tomerizations. All right, an internal rearrangement. All right, so just to summarize conceptually what we just learned here. Our alkynes will undergo hydration reactions to produce enols. However, our enols are unstable and will immediately tautomerize to produce either an aldehyde or ketone. Cool. All right, so before we move on, let's see, like, if I've given you an aldehyde, let's make sure that if I give you an enol, let's make sure that we can sort of draw our tautomerized product here. Okay, so an enol is any time we have an OH group bound to that carbon in a carbon-carbon double bond. Okay, so based on analogy of what we saw in the previous example, see if you can't draw me that rearrangement, that tautomerization product here. Yeah.
Are triglycerides alkenes?
No, those have a bunch of triglycerides. They definitely have a bunch of alcohol groups on there. I don't know. Maybe I'm mixing up glycerol with glycerides. I'd have to look. I'd have to cheat. Oh. They're yes and no. Those are like take glycerol with yes and no. They have long chains. They may have a double bond in there, but their functional groups are esters on the other end, like an ester with a long chain. Okay, so let me take my Lewis structure real quick just to kind of prove a point. All right, when I'm doing my tautomerization here, I'm going to pick up this carbon-carbon double bond here, and I'm going to move it over so that it becomes a carbon-oxygen double bond, right? So I'm going to pick up that pi bond, and I'm going to move it over. Whoops. So now I have a carbon-oxygen double bond. But what else am I going to have to do so I don't break carbon's octet rule? I got to move this hydrogen as well. And I'm going to move that hydrogen back down here so that everybody's happy and has a complete octet. All right? So the big thing about a tautomerization is you're not adding any atoms, you're not taking any atoms away, you're just rearranging things on the page. All right? So in terms of our bond line structures, I need to make sure I have the same number of carbons, those same 4 carbons. But now I'm going to draw a carbon-oxygen double bond. And I'm going to take away that hydrogen, and I'm going to move it over to this carbon. Okay, and from a bond line structure perspective, you're allowed to leave your hydrogens implied, so I can just go ahead and delete it altogether. Right? So importantly, this hydrogen does move over to this carbon after that carbon-carbon double bond gets broken. We can keep track in terms of our number of hydrogens. We can convince ourselves that in this structure there's only 1. Whereas in this structure now there's 2, so I haven't lost any hydrogens in this process. All right, but importantly, your enol, your carbon-oxygen, your carbon-carbon double bond with a hydroxyl group now becomes a carbonyl group here. What functional group is in our product here? Now, alkenes are carbon-carbon double bonds. All right, this one would be an aldehyde because that carbon-oxygen double bond is on the very end. if we did the same thing with this one, again, I'm not going to lose any carbons. I'm going to have that same 5-carbon ring there. But now my double bond is going to move from being a carbon-carbon double bond to a carbon-oxygen double bond. All right, what's our functional group in this molecule? So not an aldehyde because it's not on the end of the molecule. This one is a ketone. Ketones have carbon-oxygen double bonds in the middle of the molecule. Right, so that's why we said these tautomerization reactions will produce either an aldehyde or a ketone, depending on whether that hydroxyl group is on the very end of the molecule or sitting in the middle of the molecule. All right. So when we did this before, we just said water was being added. Let's look at our actual reagents here. Okay, we're going to take an alkyne. Okay. I guess we could say hydration reagents. All right, these have a lot of the common sort of key things that we noted about our other ones, but they're not the exact same, all right? So our first one is also going to be a hydration reagent that contains boron, and it's going to favor the less substituted carbon, but it's not exactly borane BH3. Okay, it's BHR2 in THF. Instead of having 3 hydrogens, it has an R group, which is an alkyl group, so there are some carbons on there. Does the exact same thing. So R means alkyl, meaning some number of carbons. Pretty sure it's 4 for this, but I don't know for sure. Doesn't really matter. All right, and again, what I really want you to do is not get too bogged down in this whole list here. I want you to blur your eyes and say, oh, I see boron in there. And boron is one of those substituents that prefers the less substituted carbon, or not substituents, one of those reagents that prefers the less substituted carbon. Okay, so where are we going to put that hydroxyl group for our enol? On the red carbon or on the blue carbon? On the blue carbon, the less substituted carbon. Right, so we get our hydration product, what we would expect. But again, this thing right here is our unstable enol. So what is the actual product of this reaction? Everybody take a second and let me know. Yep. there's only one product that you would get in this case here, right? Because you're going to put that OH group on the less substituted carbon, and then you're always just going to sort of move your pi bond to be between that carbon and oxygen. All right, so at the end of the day, I should have a 5-carbon aldehyde here. Where my enol has tautomerized into that aldehyde. Okay. Let's take this same one. Okay, we're going to have another reagent. We talked about how we had our mercury was the signal that it pointed to the more substituted carbon. All right, we have a little bit different looking of a reagent, but it still contains that same metal. Now instead of mercury acetate, you're going to use mercury sulfate in sulfuric acid and water. All right, and just like before, when you see mercury, you're going to think the more substituted carbon. Okay, so everybody take a second. Give me my product of this reaction. So we first get that unstable enol. That'll then tautomerize into what functional group?
Ketone.
This time we're going to get a ketone, exactly. Okay, and to be clear, the ketone and the aldehyde, these are the products of this reaction. You can't actually isolate these enols. They form, but then they quickly rearrange themselves into what your actual product of the reaction is. You can't like stop it at that middle step there. Okay, real quick while you guys pack up, let me just talk about the format of our exam here. The exam is going to be a mixture of both multiple choice and short answer questions. You'll be given a Scantron in the testing center. There will be multiple choice questions that you'll go through and bubble in your answers. You'll see that the multiple choice questions are numbered to correspond with your Scantron. But this is an organic chemistry class, and so drawing your structures is really important as well. So there will be some answers that are some questions that are labeled short answer. And you're going to draw your structure or your picture of your house in the box provided. To not mess up the numbering of your Scantron, those questions will be lettered instead of numbered, right? So your multiple choice that you'll fill in on your Scantron, A, B, C, D, whatever, you'll bubble that in. Those questions are numbered. And then you'll get to one of these drawing questions. It'll say short answer. It'll give you a space where you should be drawing your molecule in there. But to not mess up the numbering on those Scantrons, those are lettered instead of numbered. Does that make sense? Cool. If you have any questions, come see me after class. What's up?
So those will just be graded by you, right?
Yeah, those will just be graded by me.
Do you have a schedule with the testing center at all? Or?
The schedule with the test. Yeah, so if there's a page under the course introduction module, but they open at 8:30 and they pencils down at 4:30.
Okay.
Anytime in there, you can take it.
I was wondering if you could send out the questions for our chemistry project.
Send out the questions.
Yeah.
Well, so you're going to come up with the questions.